Hello everyone, and we are returning to the second part of section 2.3. As you probably remember, the theorem we stopped last time was proving that determinant of the product of two matrices is equal to the product of determinants. Now guys, I'm going to use this theorem to prove something about inverse matrix. Well, again, we can kind of distribute determinant over the product. Let's do our next theorem, and that's going to be theorem about inverses. Theorem: if matrix A, square matrix n by n, is invertible, means has inverse, then determinant of that inverse is equal 1 over determinant of original matrix. How I'm going to prove it? I'm going to use a statement of, which is next, like A multiplied by A inverse, because I'm given that it's invertible, right? Matrix A is invertible, equals what? Identity, because it's inverse. Now, I'm going to apply determinant on both sides. So determinant here, A and A inverse, and determinant here. Well, we remember that by the previous theorem in the red oval, we can distribute determinant over each matrix and kind of write down the determinant of A multiplied by the determinant of A inverse, right? And what is determinant of identity matrix? Well, we remember that for diagonal matrix, which is identity, that's a product of diagonal elements, which are equal to 1, also it equals to 1. Now I'm just going to solve this little equation for determinant of inverse matrix, and that's going to be 1 divided over determinant of A. Again, guys, you probably remember somewhere in the beginning I said we cannot divide matrices. But here we are dividing numbers. 1 divided by determinant of A, it's 1 divided by a number, which is represented determinant. Okay? Very good. So nice theorem, and we are done with it, and we are going to move to something more interesting. As you probably remember, when I was teaching you how to find inverse using identity matrix and kind of row elimination, I told you that I'm going to teach you another method of finding inverse, and that's the time we are going to do it. So I'm going to start. So that's going to be kind of method number 2, called adjoint method of finding inverse. Before we were doing row elimination, right? Before we kind of learn this method, we'll need to go like and make definition of what is adjoint. Well, I'm going to start with definition here. Let me make my squares a little bit bigger. So what is adjoint? Definition. Imagine that we start with matrix A, which is like the most general n by n matrix. And it has coefficients a11, a12, a1n, and over here an1, and lots of coefficients here, a and n. Now, let's create a matrix of cofactors. I'm going to write down a matrix of cofactors. Of cofactors. How it's going to look? I'm going to label it as C, okay? So, for example, what is cofactor of this element? Cofactor of element A11, it's actually the determinant of whatever is left when you cross it out, multiplied by -1 to the power of -1. The negative, multiplied by -1 to the power of 1 plus 1. So I'm going to label that number as cofactor 1, 1. And for every other element, I'm going to calculate cofactor and put it in the position where element was sitting. For example, here 1, 2, and here 1, and over here C and 1. Again, those C's are cofactors of their elements. Again, when do we use cofactors? We use cofactors to calculate the determinant, right? The determinant is actually, let me remind you because I'm afraid that you guys forgot it. This determinant of A expanded by the first row is E11 by C11 plus E12 by C12 and until you reach A1n by C1n. So these C's are cofactors. And we just put them instead of each element. Just remind them. So matrix of cofactors. Now guys, let's transpose this matrix and create matrix which is called adjoint of A. Adjoint of A, it's a matrix of cofactors transpose. How it's going to look? Well, I'm going to write down elements. What we do when we transpose matrix, we take the first row and make it the first column. So C11, C12, C13 until you get C1n. And then the second row, C21 and C2n. And until you kind of do all of them. So that's definition of adjoint matrix. So by definition, adjoint matrix, it's a transpose matrix of cofactors. Okay. A little bit convoluted. I'm going to show you like how it's going to work. I'll need it for my proof. Now, guys, theorem I'm going to prove. A inverse equals 1 over determinant of matrix A multiplied by adjoint matrix A. So guys, I'm giving the formula for inverse matrix. Like before, when we do row elimination, we basically cannot tell in the beginning how inverse matrix looks. Just because we're supposed to do all these row operations to get to the final result, right? Until you kind of do all these operations, you don't know how it looks. Here, guys, this is a formula. Like remember matrix 2 by 2. Maybe we should use this theorem first for matrix 2 by 2 to just verify if it's going to still work. We know that elimination works on 2 by 2, but let's check if this one is going to work on 2 by 2. And after that, I'm going to prove it. The proof is not going to be short, but let's just kind of first check for 2 by 2 if it's working. Again, that's a formula. And I will ask you to memorize this formula. That's method number 2 of finding inverse. You will need to know this. I'm going to do the check for a 2 by 2. So let's see how this formula is going to work for matrix 2 by 2. Let's use like standard matrix 2 by 2, which is A, B, C, and D. Well, first, we do know what is going to be inverse by formula, which we got before, right? We know that inverse is going to be what? You switch diagonal elements, D and A, and you put minus in front of non-diagonal elements. Let's see if this formula is going to work too. Is it going to work? Same way. And I forgot to mention 1 over AD minus BC. Sorry, that's a coefficient. Just sit over here. I don't want to copy everything. Okay, let's try to use this formula. Let's first find the cofactors matrix for this. What is cofactors? Well, remember, cofactors are just like determinants of remaining matrices multiplied by this. Minus 1 to the power of negative to the power of 1 plus 1 or 1 plus 2. So here, for example, we have the leftover determinant is just D, right? For B, the determinant is going to be just C, but it's going to be with minus because here we have like minus 1 to the power of 1 plus 2. The next one, for C, element C, if we cross it out, then determinant is going to be just B. And again, it's going to have minus. The reason is that, oh, again, the position is 1 plus 2. And the last one, for element D, if we cross it out, the cofactor is going to be A, and we don't need the minus here because it's 2 plus 2. That's a cofactor matrix. Now, adjoint. I'm going to create adjoint. Adjoint of A is C transpose, right? I'm going to do this C transpose. Diagonal elements are not going to move, and transpose is going to turn this minus C to instead of minus B and minus B instead of minus C. That's my adjoint. Now I'm just going to apply the formula. My A inverse is going to be 1 over determinant of this matrix. Well, we do know that for 2 by 2, it's AD minus BC, right? AD minus BC. Okay, kind of matching already, right? AD minus BC. Now, let's copy a joint matrix, which we have over here, which is D minus B minus C and A. Sorry, guys, I'm still a little bit sick. You see that that's exactly the same one, right? So good formula works for 2 by 2 at least. Now we are going to prove that it's going to work for any other matrix. Proof is going to require some effort. So I'm going to do it slow. If it's too slow for you, just kind of, turn it faster. So guys, what I'm going to do? Well, remember which formula I'm proving. I'm proving that inverse matrix can be represented as adjoint multiplied by 1 over determinant of A. What I'm going to do, guys, remember that the major property of inverse matrix, that's going to be the proof. Proof is going to start that kind of A, matrix A multiplied by A inverse equals identity, right? Basically, if I want to prove that this matrix A inverse is like inverse, I'll need to prove that this like product is going to give me identity. What I'm going to do, guys, if you look at this formula, 1 over determinant is going to be just a number because determinant is just a number, right? This one doesn't look like a matrix, but it's actually a matrix, right? Because we are just labeling it's a adjoint of A, but that's just a modified matrix A, right? Because we create for matrix A this cofactors matrix, and then we do transpose. So this is a matrix. What I'm going to do, guys, I'm going to start my proof with multiplying matrix A by adjoint of A. Guys, I'm going to write down adjoint from starting with lowercase a. So I don't have that many like capital case A here because my matrix is A and the adjoint starts with A and another A. So what I'm going to do, I'm going to just write down the product of matrix A by adjoint of matrix A. How it's going to look? Well, again, here there are lots of interesting things which we can see in details. So matrix A consists out of elements 1, 1, 1, 2, 1, 3, and like 1 n. And then 2, 1, and then 2 n. And eventually that's n1, and that's n1, right? Good. How my adjoint matrix is going to look? Well, adjoint matrix is going to have these cofactors, but they are, because it's transpose, it's going to have them in like columns. So for example, cofactors of elements 1, 1, 1, 2, 1, 2, they are not going to sit in a first row. They're going to sit in the first column. So I'm going to write them down. C11, C12, C13, and C1n. Cofactors of the second element, second row are going to become my second column, and they're going to be C21, C22, and C2n. And until I kind of write all down of them, right? These cofactors. So basically I just what? I took my matrix A, calculated these cofactors, and then I transposed it. Now guys, I'll need to multiply them, right? Let's see what are going to be the elements in the product. Well, since multiplication of matrices is a long story, I'm going to do it step by step. I'm going to start with the first element of the product. I don't know how to label it. I don't know, let's label it as D, for example. A resulting matrix. Let's label resulting matrix as D. And kind of, I'm going to calculate the first element of it, D11. Well, how do I do this? I'll need to multiply my first row by my first column here, right? And that's going to be A11 by C11. Yeah, it looks like 2 over here, but that's actually 1, right? And then A12 by C12, A13 by C13, and until we reach A1n by C1n. And you guys probably see that's nothing else than formula for determinant if you expand it by the first row. So this is determinant of matrix A by row number 1, expanded by row number 1. So just like if you do it, that's going to be exactly the determinant. Oh, kind of good, right? Now, what if I want to calculate my next element of my matrix D? My matrix D consists out of some elements. That's D11 and D12, for example. Next one, D12. I'm still going to have my first row, but I'll need to multiply it by the second column, right? And I'm going to have A11, C21, A12, C22, A13, C23, and A1N, C2N. Well, guys, you already seen this trick before. What we are going to have? We have cofactors of the second row. Actually, this cofactor C22, they are cofactors of the second row, but we multiply them by the first row instead of actually second row. If we had element A21 here, and we had element A22 here, it would give us determinant of A by the second row, right? But if we have different elements, like from the first row, it's going to also give us determinant, but the matrix which has 2 row 1. I'm going to write 2 of row 1, just because like matrix, well, the formula actually does not know like what was the matrix. Matrix is just taking cofactors, multiplying by numbers. But if we kind of restore it back to the matrix, it's going to look like we put elements 1, 1 instead of elements of a second row. And we kept the rest. And of course, determinant of the matrix with 2 same rows is going to be equal to 0. So here we are going to have 0. And that means that this element is going to be 0. What is going to happen to all other elements like 1, 3, 1, 4, and so on? Again, we are going to multiply the first row by non-complementary cofactors, cofactors of the third row, fourth row, and they are all going to look like we calculate the determinant of matrix A, where we have row number 1 instead of a second row, third row, but for us, it's important that because we do have same rows, first row is going to be still sitting here for all these cofactors, and we multiply by it again. We're going to have all zeros. Well, what does it mean? I'm going to go back to my matrix D and kind of make it a little bit like looking more, fill it a little bit with numbers. So that's going to be determinant of matrix A here and lots of zeros here, actually all zeros. Now, guys, I'm going to just mentally or like in my brain move to the next one, next row. What is going to happen? I'm going to have the second row. And if I multiply it by these first cofactors, which belong to the first row, it's going to produce 0. But if I multiply it by its own cofactors, I'm going to get determinant of A, right? Just expansion by the second row. And if I multiply second row by any other cofactors which do not belong to it, then I'm going to get a bunch of zeros again. And what we see, guys, we get determinants only when number of the row is matching number of the column. And here 1, 1, 2, 2, and eventually we are going to have another determinant at position 3, 3. And you probably understand that all positions are diagonal position. So that's why I probably labeled it with letter D, diagonal matrix. So this product, I'm going to write down, product of A by adjoint. I'm going to write it down one more time. A by adjoint of A. Actually, equals the very weird matrix. It has determinant of A on main diagonal and zeros everywhere. Oh, I'm going to just label all zeros with 0. Well, for us, it's going to look like we took an identity matrix and multiplied it by determinant of A, right? If we do identity matrix 1, 1, 1, 1, 1, multiply by determinant of A, you multiply by that number all elements, which are going to be always ones, and we are going to have this result. So now, if I want to just move this determinant over here. Well, that's a number. We know that it's not equal to 0 because no, we don't know it's not equal to 0, but let's consider that it's not equal to 0. We're going to move it here, and we are going to write down A multiplied by adjoint matrix A divided by determinant of matrix A equals I. So what we see, we have matrix A, and we have some other matrix, which is like a complicated formula, equals identity. Then, by one of the theorems we proved before, that's inverse, because like we proved that, like if we have matrix A multiplied by B equals identity, B is inverse. We don't need to check two things. That's inverse. Okay. So what is going to be conditioned to have inverse now? If we go back, because I said that we don't know yet if determinant is equal to 0 or not equal to 0. So when I started proving my theorem, I actually just gave you the formula. I did not place any conditions on matrix A. But from this formula, it's obvious that we cannot have determinant equals to 0. So that's going to be our condition for the theorem. For a square matrix A by n, A n by n, with determinant of A not equal to 0, the theorem is true. And because a theorem is kind of implying that determinants are not supposed to be equal to 0 because we are dividing by it, that's just a very one small condition. Right? Okay. Well, I think we proved a very important theorem, and that's a nice way to find actually inverse matrix using adjoint matrix. We do know how to calculate cofactors. For 3 by 3 matrix is not going to be too difficult. We are going to have examples in class, and like for right now, I'll need to prove one more theorem before we kind of finish our lecture. Well, very nice. So we proved how the matrix is going to look. Inverse matrix. I'm going to write it down one more time, copy it over here. So if matrix A has inverse, inverse is going to have a next formula. And when it has inverse, when determinant is not equal to 0, right? A inverse equals 1 over determinant of A by adjoint of A. Well, again, we remember what is adjoint. Now, guys, we're going to use this formula to introduce Cramer's rule. Cramer's rule. Well, Cramer's rule, remember, Cramer's rule tells us that we can calculate, we can solve actually non-homogeneous system of equations. If you remember from previous classes, of course, it's not necessary to solve the whole system. We can solve it for particular variable. For example, you have 25 variables in your non-homogeneous system, and you can solve it for variable number 3. You don't need to know all of like solutions, we just can solve it for variable number 3. That's the essence of Cramer's rule. Before we kind of use Cramer's rule, we'll need to kind of prove it first, right? And so give me a second. I'm going to copy Cramer's rule. It's going to take a little while. So if AX equals B, non-homogeneous system of equations, which has n unknowns, and determinant of A is not equal to 0, then a solution, I'm going to put like exclamation mark to say unique solution. This system is going to have only one solution. Solution is going to look like this. X1, the first unknown, is going to be equal determinant of special matrix A1 over determinant of matrix A. I'm going to explain what is A1. X2 is going to be determinant of matrix A2 divided over determinant of matrix A, and so on. So actually you can give a formula to calculate one variable. What are matrices A1, A2, and so on? These matrices are obtained by replacing A1 is matrix A, where column C1, first column, is replaced by, by column B. A2, that's the same, but C2, column C2, this is not like cofactor, is replaced by column B. So you kind of take column B and start replacing columns of original matrix with it. Well, I don't know, maybe I should give like maybe one like visual example of how it works, okay? I'm going to I'm going to consider a very, very simple system. So my matrix A is going to be 1, 2, 3, 4, 5, 6, 7, 8. Guys, I'm going to put 0 here because if I put 9 here, the determinant, I'm afraid, is not going to be equal. No, it's going to be equal to 0. And we have x1, x2, x3, and the B column is 1, 2. So this is my A, then my X, and this is my B, right? So I'm not going to actually solve, but what I'm going to do, guys, I'm going to show you how to form matrices. So this A1, A2. So matrix A1 actually is going to look like I take my original matrix A and take the first column and place actually column B instead of it. So I'm going to have 1, 2, 3, and here 2, 5, 8, 3, 6, 0. Okay, now A2, A2. I'm going to take this column and put it instead of the second one. So I'm going to keep the first one, 1, 4, 7. And instead of second, 2, 5, 8, I'm going to put 1, 2, 3, and 3, 6, 0. And that's how we build these matrices. And basically after that, you just calculate determinant of this matrix and calculate determinant of original matrix. And that's going to give you, divide them, and that's going to produce a solution. Well, we are going to work on exercises in class. Now I just want to kind of verify or show you why it works and how to prove it, okay? It's not going to be very difficult to prove why it's going to work, and that's such a weird formula. Well, guys, we know that if determinant of A is not equal to 0, then A inverse exists, A inverse, right? And we can use this adjoint formula to do it. So determinant of A multiplied by adjoint of matrix A. Okay. Well, what I'm going to do, I'm going to write down the equation AX equals B, and I'm going to multiply it by A inverse on both sides. A inverse by AX equals A inverse B. Well, we had this formula a long time ago. Now I know that this is identity, and my solution is going to be actually what? A inverse by B. This is just a reminder why it's looking like this, and I hope that everyone still remembers this. What I'm going to do, guys, I'm going to use my formula and multiply it by B. And later I'm just going to check each column, okay? You know that X here is not going to be like actual as a rectangular matrix. It's going to be just one column of elements, right? So actually X here, it's just like X1, X2, X3, the answer. I'm going to continue on the right side with copying like this expression 1 over determinant of A multiplied by adjoint of A and multiplied by column B. Well, I'm placing the bar above it just to verify that it's column. Okay, so what I'm going to do, guys, I'm going to continue here, but I want to actually put matrix instead of A adjoint, right? I'm going to copy. So it's 1 over determinant of A. And here I'm just going to use actual matrix, adjoint of A. Remember, adjoint consists out of cofactors, but they are sitting in columns. So I'm going to put C11, C12. So generally, these are cofactors and they're supposed to sit here in first row. But because it's adjoint, I'm placing them in columns. 1, 3, and C1n, and C21, C22. Oh, instead of C22. C2. Okay, and that's going to be the column B. Instead of column B, actually, I'm just going to write down the column B. I'm going to be looking better. B1 and over here Bn, right? Now, guys, when I multiply these two matrices, because the B matrix has only one column, I'm basically going to multiply first row by this column, and that's going to produce for me the first element here, x1. Well, multiplying also by this element, like this coefficient. So that's what I'm going to do. I'm going to write down my first element, x1, is going to be what? 1 over determinant of A, which is like a coefficient, multiplied by C11 multiplied by B1 plus C21 by B2 plus C31 by B3 and so on. Well, guys, this probably looks a little bit weird. We were expecting to multiply cofactors by the column to get some determinant, right? Well, what we have over here, let me use orange color. What cofactors we have over here? These cofactors belong to what? They are complementary to first column. Because this is C12 and C21. So if that was not transpose matrix, that was the first column cofactors. These cofactors in like when you do cofactors, they're usually sitting here. So they are complementary to first column. So it looks like over here you are calculating determinant, but instead of first column, which is supposed to be like the numbers here, which is supposed to be like A, The first column is 1, 2, and here was supposed to be A, 2, not 1, 2, 1, 1, sorry. So write that 1, 1, first element. A, 1, 1. And then A, 3, 1. If I had these A's instead of B's, that would be determinant of matrix A. But because I have B's instead, it looks like I took these A's out, took them out, and put B's instead, and got the determinant where my first column has elements B1, B2, B3, so which is matrix A1, where you kind of substitute the first column with elements B. And all others are going to be calculated same way because these are cofactors of the second column and they are multiplied by b's. So for us, it's going to mean that you put b's instead of second column, calculate the determinant of the matrix. So that's basically a proof. Because what we do have this part, which is 1 over determinant, right? And we do have this part, which is going to be determinant of matrix A1 or determinant of matrix A2 and so on, which is actually our kind of formula, Cramer's rule. Determinant, the first element is going to be determinant of matrix A1 over A, and like second element is going to be, well, actually here we are just going to have n elements, and each of them is going to be divided by this coefficient 1 over determinant A. Well, we kind of proved Cramer's rule. I don't want to solve any problems in Cramer's rule. Hopefully we can do this in class. But if you guys still need like more understanding of how it works, I suggest you to consider example from the book and just try to do it once. And of course, in class, we are going to try to find inverse, use Cramer's rule. So that was just theory. What I'm going to do, guys, I'm going to close these brackets because that's just like actually a column of something. And that's going to be end of my lecture. I proved my Cramer's rule here. Okay, that's all.